ARM designs processors and various components that silicon designers need and licenses these designs to various silicon design companies, including microcontroller vendors. ARM does not make its own microcontrollers. ARM only will design the various components and processors, so the layout, okay. So the design will be made by ARM. So ARM will make the design and sell it to a silicon designer who will in turn get it fabricated. So they will contact the foundry and they will get those chips fabricated and then sold. ARM doesn't directly sell chips, though there are some evaluation kits that ARM has, which ARM sells. So, but that is very few. Most of ARM's business is selling the IP to these silicon designers. That is, they license the IP and they make money from there. So their money is made from IP licensing. A typical microcontroller, actually the core of the controller only takes a small part of the silicon area. The other areas are taken up by the clock generation unit, distribution logic, system bus, peripherals, hardware units, and so on. And many microcontroller vendors, though they use ARM Cortex-M processors as their choice of CPU, the memory system, memory map, peripherals, and operation characteristics like clock speed and voltage can be completely different from one product to another. This allows microcontroller manufacturers to add additional features in their products and differentiate their products from the others in the market. So even though multiple microcontroller vendors are going to use the same Cortex-M4 core, so microcontroller vendors, the core is Cortex-M4, say. But what surrounds this Cortex? So you need to have memories and you need to have different peripherals, and this will have different characteristics and so on. What surrounds these processors are completely up to the silicon designer. And what differentiates one silicon designer from the other is mainly these peripherals and memory and other aspects of the ARM core. Because the core remains the same, all of these change. For example, a TI Tiva series microcontroller, though sharing common characteristics with STM-F4 microcontrollers, will be still quite different. Some Cortex-M4 vendors are Analog Devices, Atmel, Cypress, Energy Micro, Freescale, Fujitsu, Holtec, Infineon, Microsemi, Melander, NXP, Samsung, Silicon Laboratories, ST Microelectronics, Texas Instruments, and Toshiba. Cortex-M has a Harvard bus architecture with unified memory space. Instructions and data use the same address space. Now, this definition could be confusing. For those of you who are aware of the difference between von Neumann and Harvard architecture, let's briefly see what a von Neumann and a Harvard architecture is, and then we'll go further. So, if you have a CPU here, and say you have a program memory, say it's a flash, and then along with the flash, after the flash area you have some RAM, something like that. Okay, and this is an address space. For von Neumann architecture, you have an address bus and you have a data bus. So that is the same for all architecture. But in the case of von Neumann architecture, you have the entire address space being addressed by these two buses only. So there is one channel. Which spans across all your program memory, data memory, and so on. One address channel. So if you are accessing if you're accessing an instruction, say, at that point you cannot access some data simultaneously because you're busy, the bus is busy with accessing instruction, and it is just one bus which is accessing either a data or an instruction. Okay? That is your von Neumann architecture. It's one at a time. In case of Harvard architecture, say if you have the processor here, and so microprocessor unit, and you have, say, a flash memory or some other memory which has your program, and you have a RAM, and they are in separate spaces. So this memory, this is not continuous. There's a gap between this. Okay, so this ranges from one address space to the other, and RAM has a different address range. The MPU or the microprocessor, the microcontroller unit, has a separate bus going to the instruction memory where you have the instructions, and it has a separate bus going to the data memory. Now, when I say a separate bus, it could be that this memory, so this could be 0 to some memory location, and this could again repeat from 0 to some memory location. So this need not be continuous. Okay. The advantage of a Harvard architecture is, as you can see, so there is an address and data bus here, and there's an address and data bus here. So it's a redundant bus. So if when you are accessing something from here, that is from the, say, from the flash memory, some instructions, at the same time you can access data also, because these are two separate buses, which the von Neumann architecture could not do. Now, when I said separate memory, spanning separate memory spaces, for example, this has a separate memory address and this one, and that is possible with Harvard architecture. In the case of ARM, it has a unified memory space. Unified memory space would mean that even though separate buses go to the flash and the RAM, say, or the SRAM, the address space is continuous. For example, it starts from 0 and it goes up to 4G, or it's 0 0 0 0 0 0 0 0 to F F F F F F F F hex. So it's a continuous, even though there are multiple buses, it is over a continuous address space within which you have the RAM and the flash. So that is called the unified memory space in the case of Cortex-M4. Of course, ARM takes advantage of the Harvard architecture, and its operations can be sped up because if it is possible, then it will start accessing data even while it is fetching instructions. So that's what this means. Now, and the lower Cortex M series are all von Neumann architecture, and Cortex M3 and Cortex M4 are Harvard architecture. So again, so Cortex M0 and that family is von Neumann. Cortex M3 and M4 are Harvard. And we are studying this. Since we are not studying Cortex M0, we will not talk about von Neumann architecture here. Okay, now 32-bit addressing, so supporting 4 GB of memory space. So we know about that. We just mentioned that. So it is all 8 zeros to 8 Fs. So an interrupt controller called nested vector interrupt controller, supporting up to 240 interrupt requests and from 8 to 256 interrupt priority levels, depends on the actual device implementation. Now, this is a very powerful feature of the ARM controllers. It supports a lot of interrupts, and there are 8 to 256 interrupt priority levels. So the interrupt handling in Cortex M processors or Cortex M series processors are primarily handled by the hardware. A greater portion of it is handled by the hardware, and the architecture of the interrupt handler is such that it aids writing your code in C rather than assembly. So in the upcoming segments, we will be actually going very deep into this nested vectored interrupt controller feature, and we will see how the interrupts behave in the case of Cortex-M4. Now, on-chip bus interfaces based on ARM, advanced microcontroller bus architecture technology, which is called AMBA technology, which allow pipeline bus operations for higher throughput. Now, this is something that we will also see. So, we have separate buses on the controller. They are called the AHB bus and APB bus. And in the case of our controller, we have AHB1 and AHB2 and APB1 and APB2 buses. Buses are nothing but data paths, and these buses will have different speeds also, which they can support, and different peripherals and other parts of the controller are connected to these buses. So we'll be having a look at this architecture in the upcoming slides. So, and these buses are quite fast. Some buses have limitations of how much clock speed you can supply, but other buses, the primary buses, can actually operate at 100 megahertz. So that is quite fast. So it has a pipelined architecture. It has a 3-stage pipeline, which makes instruction execution even faster, and the processor faster overall. The clock speeds can be higher, and we will talk about the 3-stage pipeline as well. 3-stage pipeline, a pipelined instruction execution means in every clock cycle there can be 3 instructions being processed. So in every clock cycle, one instruction is going to be fetched from memory, another instruction is going to be decoded, and the third instruction is going to be executed. That, and all of this is going to happen in one clock cycle. So if you have, so this is one clock cycle. So within this clock cycle, we'll have a fetch, we'll have a decode, we'll have an execute, whatever is the clock cycle. So if it is at say 84 megahertz, if the speed of the controller is configured to 84 megahertz, the time taken for one clock cycle is 1 over 84 into 10 to the power of 6 hertz, right? So this many seconds is the time taken for executing 3 instructions. That is not executing them, but fetching, decoding, and executing. So we'll have a look at the 3-stage pipeline slightly later. It has sleep mode support and various low power features. So I'm not talking much about that here because I have a slide dedicated to this. It has support for an optional memory protection unit to provide memory protection features like programmable memory or access permission control. So there are regions of the memory that you can protect in this controller, which will allow security. It supports various features for operating system implementations such as systematic timer and shadowed stack pointer. So OS does not mean a desktop OS or an enterprise OS. This means a real-time operating systems. C-friendly and easy to use, makes software portability and reusability easy. Support for a bit-wide data accesses using a feature called bitband. So there is a feature called bitband whereby you can actually access bit-wide data for it. So you don't have to access a byte or access a word and then extract your bit from there and do a rotation and all that. You can actually extract individual bits from a particular location. So bit banding is not allowed in right across the memory map, but it is allowed for certain locations. Now, option of being used in a single processor or multiprocessor designs. So if you work with a multiprocessor core also, so Cortex-M4 allows that flexibility also for a silicon designer to have a die with multiprocessor cores, and it has a hardware floating point unit which is Cortex-M4 only. So hardware floating point unit means you need not use soft floating point, soft float, that is floating point implementation through software, because if you implement floating point operations through software, it is expensive. There's a lot of software that goes into implementing a floating point operation. So rather than that, it has a hardware floating point unit which is much faster. So if we say we feed different floating point numbers into the floating point unit, and whatever calculation we do, the floating point calculation is done in hardware. So the load of the calculation is taken care of by the hardware, so that we don't have to write complicated software to perform the same operations, thereby saving time and power. So the three-stage pipeline allows for execution of almost all instructions in a single clock cycle. The processors can run at 100 plus megahertz. Since the processor does more work per clock cycle, it could run at lower clock speeds to conserve energy while still getting significant processing done. So if you compare a ARM 32-bit controller, say, so this is Cortex, so this is a Cortex-M4 core, M4, and say this is another 32-bit microcontroller. We don't say what, we just any 32-bit microcontroller, and say both are running at 100 megahertz. We see that the Cortex-M4 is capable of taking up greater workload than this 32-bit controller at the same clock speed, because all instructions are single clock cycle instructions. So even though both are running at the same clock speed, the amount of work that a Cortex-M4 does is much higher than a comparable 32-bit controller. So this is not always true. This is not a sweeping statement saying that it is better than any controller 32-bit controllers out there in the market. But then again, this is the general trend. Since the processor does more per clock cycle, so we saw that Harvard architecture allows for simultaneous accesses to instruction and data memory. So we saw that the pipeline bus architecture for a higher frequency in the memory. So since it is a pipelined architecture, as we saw, it allows a higher frequency of memory access. Complex operations can be carried out with lower number of instructions due to instruction set efficiency. So the instructions, it is RISC, and each instruction is very powerful and efficient. So with one instruction, we can carry out higher number of tasks. So complex operations can be carried out using these instructions because of their efficiency. Since every instruction fetch is 32 bits and almost all instructions are 16 bits, two instructions can be fetched at a time, allowing better performance. So since we are using the thumb 2 instruction set, and most of the instructions will be 2-byte instructions. So most of the instructions are going to be 2 bytes. That is half word. So if it's half word, the ARM processor accesses the address at word boundaries. So accesses the address space at word boundaries. So you could have, this is half word and this is half word. So all together 4 bytes. So it accesses 4 bytes, but when it accesses 4 bytes, it will be accessing 2 instructions basically. So at every fetch, it is accessing 2 instructions if the instructions are 16-bit. The thumb instruction set on the ARM Cortex-M4 allows higher code density, of course, because the instruction set is powerful, and on top of that you have 2-byte instructions. So obviously for example, any processor that is supporting say a 32-bit processor which is having a word length instructions will of course fit in lesser number of instructions within the same memory area. Now you might wonder what difference does it make if the other processor is taking up a little bit of more memory. How does it matter? For example, say whatever ARM can say fit within say 256 kilobytes, the other processor or a competitor probably would need 400 or 500 kilobyte to amount of same amount of code. Now the advantage of having a lesser, so don't think that since you have got a processor or a controller with a lot of flash in, you are at an advantage. That is not always the case. Higher flash means higher power drain, and of course higher cost also. So if your design can make do with smaller amount of flash, it will amount to low power consumption and cost saving. Okay, so if you have another processor which is using a greater amount of flash, it uses greater amount of power, and it is costlier also. So we'll have to, so whenever we are building a product, we have to keep all of this in mind.